evening, everybody, and welcome to tonight's edition of the Triangle Area SQL Server User Group's main meeting. So we have with us the one and only Peter Shore, who is going to talk to us about wait stats and other fun things tonight. So without getting too far afield, let's hand it straight off to Peter. So please, take it away.
Thank you, Kevin. Other fun things may include terrible dad jokes that are not actually funny, but they will be, within reason for the audience. So I won't say anything bad except for the quality of the joke being bad. So this is a session called Wait, Do Tell Me, and we are going to talk a little bit about wait stats in SQL Server. But a little bit about me. I am a SQL Server database administrator at your favorite burrito retailer. At least I hope it's your favorite burrito retailer. And if it is, thank you. I would call myself an intentionally accidental DBA only because I did everything that looks like an accidental DBA, except I'm just goofy enough to have done it on purpose. I am the organizer of the user group here in Columbus, Ohio, and the co-organizer of SQL Saturday Columbus. Pardon me. You can find me at pshore73 on Twitter and pshore73 at outlook.com via email. So the question we all get is, why is it taking so long? Probably with more wine than what I just used. And the reality is, to look at the runtime is just not enough. There's so many factors, of course, that can make the runtime vary. It really helps to know the time that we spend in the phases of execution. The time creating the plan, the time doing the actual work, and then there's this other bucket of other things when we're just standing around waiting, or whatever the digital internal of a computer equivalent of standing around waiting is. And believe it or not, in 2003, and yes, this paper is still relevant, Tom Davidson published SQL Server Performance Tuning using weights and queues. Things have changed, right? There are a lot more wait types. There's a lot more stuff in SQL Server, but the basic concepts of this white paper are still valid as we go ahead and start to look at performance. To counterbalance it, though, Greg Gonzalez published a blog post as to why wait stats alone are not enough. So while I'm focusing on wait stats enough, I will occasionally remind you that we should not look at them, blindly. I want you to keep that in mind, that wait stats are very useful, but they're only one source of information. So what is wait time? Well, all these definitions are various ways that we can describe wait time. And in the end, it's, I like the last definition, the accumulated wait time spent waiting broken down per resource. And that broken down per resource part really helps from a troubleshooting perspective. And just to note, anything that a thread is waiting for is a resource. And that probably begs the question, just what is a thread? So threads are subsets of processes. And they all act and live in a shared address space. And the reason we use threads is context switching is faster between threads than spinning up a new process. Threads are the smallest sequence of instruction that can be managed. And threads are managed by a scheduler. That does imply that there are smaller sequences of instructions, and they're called fibers. We can't manage them. It's a trivia answer as far as I'm concerned, and I'm just nerdy enough to be into that kind of trivia, but we're not going to talk about fibers tonight other than these couple of sentences. SQL Server has a maximum number of threads based on the number of logical processors, and we'll see a chart of that here in just a moment. And just a moment has arrived. So remember, the logical processor is the hyperthreaded processor. So we can get 2 logical processors per physical core, even if they're not a 50-50 divide. And this chart from Microsoft shows approximately how many worker threads we get per our CPU configuration. So we have a scheduler, and that scheduler is a piece of software that manages threads or processes. In SQL Server, it's a one-to-one correspondence of scheduler to core, and in fact, they're often used interchangeably in conversation, even though that's not technically correct. Now, just because there's a one-to-one correspondence doesn't necessarily mean that a scheduler is bound to a specific core. The schedulers will change which cores they run on. That change within a given process is called context switching. When it comes to thread switching in and out, Windows and Linux schedulers are preemptive, so something can interrupt them. SQL OS, for those of you who are not aware, there is an operating system within SQL Server, and it is non-preemptive from a thread perspective. So there have to be parameters around the way threads stop. They're not interrupted. Within SQL Server, the schedulers, along with memory disk access, are managed through SQL OS. SQL OS then asks Windows or Linux for what it needs. I like to joke that SQL OS constructs an appropriate lie to Windows and Linux to get what it wants. And I'm going to guess that Windows and Linux tell some lies back. So if you want to look at threads, schedulers, workers, and tasks on your SQL Server, there are DMVs for each of them. I don't show a sample of them because really the output is kind of boring, and you're only going to look at these when there's a reason to look at them. Now, the DMOS schedulers DMV will tell you if a scheduler is offline, which could be impact of a wrong license being applied, which is a little bit of administrative trivia that may solve a problem for you, so I'll share it. But otherwise, I find these DMVs by themselves not overly useful. But their existence is very useful if you start joining them and looking for problems and joining them with other things. Now, when we talk about threads, they can be in one of 6 states. But the reality is, for our context, we're only concerned about 3 states: runnable, running, and suspended. Okay, I suppose to some degree, in the end, we really care about done because we want our work to get done. But if it's done, it's not causing us any problems anymore. So we're going to ignore that one. As it says there, running or runnable, it's waiting for a quantum, which is the time given to a CPU, a thread, for use of the CPU without interruptions. Running is running is running is running. And that means the executing, doing stuff kind of running, not the pick them up, put them down, like run, exercise kind of thing. Because if it were that, I wouldn't talk about it. And then suspended. But that officially means it has a worker and it's waiting for an event. Or it's waiting for a resource is probably the way to understand it. Technically, an event happens that says the resource is available, and that's why it's waiting for an event. Threads can leave the running state because it completed. It has a need for a resource, or it reaches the end of the quantum. Quantum in SQL Server is a hard-coded 4 milliseconds. You can't change that unless you work for Microsoft and have access to the code, and probably somebody's going to want to approve changing that. So to kind of get a picture of this, my lovely art skills here. Down in the lower left, the runnable area is a queue. It is a traditional queue. It is first in, first out, order matters. Running is running is running. It's doing the voodoo that we've told it to do. And then the suspended or waiter area is a list. And the difference between a list and a queue is a list is not ordered. So it does not matter when something got on the waiter list. As soon as its resource is ready, it can go to the runnable queue. It doesn't have to wait for other things to come off. And we can see that. We saw 73, speed 73 was in the running. It now is waiting for something. So there was room on this scheduler. Thread 87 went up there. And at the same time, 151 was signaled that its resource was available. And to illustrate the idea that moving off of the suspended or waiter list is not ordinal by entry time, it looks like our friend 73 was able to get the resources it needed, and now it's sitting on the runnable queue, while 103 is running and 87 is waiting. Now, 73 could have been signaled without 87 coming off. I just happened to choose in my illustration to move some more numbers around. Any questions at this point?
No questions yet, but if there are questions, chat, let's get them in, and I'll make sure we give Peter the time to take a drink.
Yep. So SQL Server measures wait time by design for every resource wait. And that by design piece truly means that the product team at Microsoft wants to measure this wait time for every resource. Why do they care? Well, it helps them solve problems in the engine, solves problems in their code. As a result, it also helps us as DBAs and data professionals see where we have problems in our code, or in my world, in the case of my BI team's code. There will always be waits. Therefore, there will always be a top wait because they're numeric and we can order them. I like to talk about these two together. There will always be waits. I mention that because I have been in that conversation and heard of others being in that conversation, where usually a manager says we have to get rid of all waiting in SQL Server. And that's not possible. We can absolutely work to minimize the waits. There will always be waits. There are always going to be times where we wait for resources. And as such, there's always going to be something we can put at the top of the waiter list, which is always a good place to start. Let's troubleshoot our most frequent wait and see if we can reduce it and minimize it. However, we also have to understand that some, and really by some, I mean many or even most waits are benign as it pertains to performance. They just aren't performance affecting waits. They're part of those things that the telemetry in SQL Server is measuring. So the dev team can look at that telemetry and evaluate their performance of their code, and it doesn't in the end impact us. Again, waits should not be analyzed in isolation. And this is relative in two ways. One, it's not just waits. We need to look at all of the other performance counters and things that we can measure and look at within SQL Server and the underlying OS. But we also want to make sure that we're not focused on an individual wait statistic, because many of them are best troubleshot in conjunction with one or more other ones, because we get more information that way. And some of them, and we'll talk about one of them, isn't really a problem to spend a ton of time on unless it is in conjunction with another one. So in the end, we're data professionals. Look at the daggum data. And part of that data is a baseline. We want to baseline all of our performance, of course, but we really want to baseline our weights so we can define normal. And I want to be very clear that normal just means what's consistently happening on that particular instance. It's not good, it's not bad, it's just normal. It's just what typically happens. Instance A to instance B is probably not going to look the same. In fact, I'd be rather surprised if it looked the same. When it changes, we can then, because we are looking at this normal baseline and we know where it ebbs and flows, when we see a stark difference, we can identify changes. We can say, oh, it was Tuesday night, there was a deployment, the performance got worse because somebody's code went in. We know when that started. Oh, the performance got better because of their code. The performance got better because we added those 12 indexes that weren't there before. Or performance got better on a bunch of inserts because we got rid of a bunch of indexes. In the end, what usually happens, and then identify changes. We can look at weights through DMOS waiting tasks, which will show you what's waiting right now. So if somebody calls you and says the SQL Server is slow right now, you can look at DMOS waiting tasks. I would actually use one of the other ways, Atom Mechanics' wonderful procedure, SP Who is Active. I personally, every time I run it with at least the find block leaders and the get plans parameters on. It is free. Follow your appropriate change control processes before putting it into your production environment. But it's fantastic. It will list all the things that are running, how long they've been running. It'll give you what it's waiting for, if it's waiting, and a whole bunch more information. I would demo it for you, but I don't have a huge workload right now to test it with. And if I gave you a screenshot, and I've tried to do the screenshot thing before, I have to block out so much to not share, proprietary stuff that it becomes worthless. So if you're not using Who is Active, go install it on a test machine and take a look at it. I think you'll find it very useful. You can also look at DMOS wait stats, which holds wait stat history. This gets cleared every time the instance restarts. If you want to see something a little more analytical on SQL Server wait statistics, Paul Randall from SQL Skills has a blog post called Tell Me Where It Hurts, and he keeps the query that he has in there updated, and it will pull back your top 95% of weights. It will filter out the benign weights. It by default filters out all of the HADR weights for AGs, but you can just comment those out of so they show up. And in fact, that I have a result set for, because there's nothing here that you can really identify any system with. So this is a system that I have worked on before. And you can see the weights, and you can see the total wait time, the resource wait, the signal wait. Now, I should note the DMOS wait stats only stores the total wait time and the signal wait time. Signal is the time that's sitting on that runnable queue because it has been signaled to move from the waiter list to the runnable queue. Simple math says, of course, we can calculate the resource wait time. It's subtraction. We can use the world's most expensive calculator. I'm stealing that quote from Joey D'Antoni. SQL Server would be the world's most expensive calculator to do that math. Paul's query also tells us the total number of times that wait was incurred since the last time the instance was restarted, and what percentage of the weights that are. You can see in this case, CX packet is my big wait. The helpful URL on the right is the link to the description of that wait type in Paul's wait type library, which is the best wait resource on the internet. It is better than Microsoft's own docs on the weights. Any questions?
No questions thus far.
All right, so let's talk about weights. Those of you old enough can put that lyric to the music of a particular song, and you'll be happy I'm not singing. So CPU weights. I bring back a copy of my lovely blue triangle, just so you are visually remembering running and runnable. We're ignoring the waiter list down on the right. So SOS scheduler yield is never on the waiter list. It's not a true wait. What happens is the SPID moves from running to runnable for one of two reasons generally. It can either be the thread has exhausted that 4 millisecond quantum. This is the overwhelming majority of the times you see SOS scheduler yield. The atypical, unusual version of seeing this is when a thread is spinning on a spin lock and has to back off. You're probably going to have some other fingerprints to lead you down that path. It's most likely, I almost said almost certainly, and that's not quite true, but it is highly likely to be the exhausted quantum. What it is not is a sign of CPU pressure. All right, scheduler yield does not mean you have CPU pressure. The way you find the queries are you're going to look for plans with long scans that also have no page IO latch waits. We'll talk about page IO waits here in a few minutes. So those table scans, nothing in the way, not waiting for anything, just takes longer than it has to do the work. And really, you're going to remediate by reducing the work for the query. You're going to, in a lot of ways, take performance tuning steps. Do I have a good query? Do I have good indexing? Reduce the work it has to do overall. And you'll see that a lot. A lot of remediation of the things we're going to talk about tonight involves some variant of reduce the work. SQL Server, like a good DBA, it works very hard to be as lazy as possible. All right. Thread pool weights. These are my least favorite weight in SQL Server. These are scary to me, and the reason they're scary is because they can bring a system to its knees. So remember we talked about threads and the max number of threads that SQL Server has. The number of threads are calculated as plan and query. The number of threads needed to run a query is calculated during the process of creating the plan. The thread pool, not all of the threads are available at any one time. The pool will grow if there are not enough threads available, as long as the threads stay under the maximum number. Therefore, obviously, the thread pool grows and shrinks dynamically. As long as, again, we don't hit that max worker threads. And shrinks in this case, it's not like shrinking a data file. Shrinks in this case is perfectly fine. If we get to that point of thread pool weights where we're talking about no available threads, queries aren't going to be able to run. We're not going to be able to log in to see what's going on. So I want to say it is normal to see very short duration thread pool weights. That's the whole expansion of the pool spinning up threads, as long as there are threads available. When there are no threads at all available, we're talking about thread starvation, and that is not normal. To get into the analysis on this, you need to make sure the dedicated admin connection, which is on by default, has stayed on, that somebody hasn't decided to turn it off. And I would strongly recommend RDAC, the remote dedicated access connection, is enabled before you have problems, of course. The RDAC simply so you don't have to RDP into the server first. Find what's running. This is where SP who is active would really shine. especially when we start talking about the fact that we need to look and see what the lead blocker is. Yeah, we can find it in waiting tasks, but if we run that find block leaders and SP who is active, we'll see. We'll find it very quickly. It'll be the one thread that has nothing blocked, or one of a very small number that has nothing blocked. And the first step of recovery is, can we kill that thread? Sometimes the answer is yes. Sometimes the answer is no. We also, of course, when killing a thread, have to consider what are the rollback implications. Can we wait it out? Do we know what this query is doing? We know it typically doesn't run very long. Can we wait it out? Do we have time to wait? Are we in a maintenance window? Do we have time to wait it out? Is it overnight? We really don't do much processing overnight. There are reasons we can wait it out. Most of the time, the reality is we cannot wait it out because it is a retail website. It is Black Friday, and we have a bad query. Yes, this is leading into a story, and we can't wait it out. Also, can we disable some workload? Can we stop piling on? In that situation where we had workload that we couldn't stop, it was in a heavy sales period, we ended up having to fail over our cluster yes, we were physical on-prem. We failed over our cluster to kill the problem, because that was the only way we could kill it at the time. Now, fixing it, fix the code. Make sure that we've got good and only the necessary joins. Make sure that we've are filtering in our predicate so that we are pulling back the smallest amount of rows in the result set. This is always good coding practice. We want to pull back the least amount of data we need in order to do the job that's being asked of us. Address indexing. Make sure we've got appropriate indexes. When we're addressing indexes, always look to get rid of duplicate indexes and overlapping indexes and unused indexes, which are not necessarily going to come into play here, but they come into play in another wait type later. And I did those two things, and I still had a query. They made it better. I still had a query whose cost for the query plan was over 2,000. It's running tens of thousands of times in a relatively short amount of time. And when you look at the query plan, you see that only one thread is doing work. I called it the Department of Transportation or the Highway Department query because it had 7 people holding shovels and one person actually using the shovel. And it turned out that the next bullet point was my problem. And it wasn't that my statistics weren't being updated. My sample size was bad. I needed to not use the default sample size. So when we think about statistics health, we don't want to just be making sure we're updating statistics. We want to be looking at our queries and testing ahead of time, ideally, to see if perhaps they run better when we have a bigger sample size. If all of that still doesn't fix the problem, you might need to address hardware. You might need more cores and to get yourself a bigger thread pool, which, of course, sorry to say, means more cost, both from a core, hardware perspective and from a SQL Server licensing perspective. Don't jump to hardware first. Look at the other things. The first 3 things cost development time, DBA time, but no licensing and hardware costs. That last one does have those problems, but it might be necessary. Any questions on that set of weights?
Let's see if anybody's got any questions there. Looks like nothing so far, so you are good to go.
All right. CX packet and CX consumer. Largely, the presence of these weights simply mean you're having parallelism. Congratulations. Hope you've set a max stop higher than 1, and you've set a cost threshold. CX consumer is the control thread weight, but we don't see this weight type until SQL Server 2016 SP2 or SQL Server 2017 Cumulative Update 3. And it can generally be ignored. There are some very specific situations, which I believe Eric Darling has blogged about, where you can't ignore it, but they are very specific situations, so I'm not going to talk about them today. Back in the day, CX packet was both the producer and the consumer side weight. Right? So CX consumer is the consumer weight. It is waiting to consume everything from the threads. When CX packet was that, it was generally able to be ignored. Now, CX packet can actually be a problem. I should, in case anybody's wondering, the server that I took that screenshot from earlier that had a ton of CX packet weights is still on SQL Server 2014. So I'm still looking at CX packet being mostly okay. Pardon me. In today's world, if you're on the current versions of SQL Server, you may be looking at skewed parallelism. So the parallelism is not necessarily happening the way you want it to. But even then, regardless of the version of SQL Server, if you're getting a lot of CX packet correlated with a lot of page latch and page IO latch, it's likely that you have an actual problem and something you need to deal with. All right. So when we talk about CX packet and CX consumer weights, please avoid the knee-jerk answer of saying max stop equals 1. Yes, it absolutely gets rid of CX packet and CX consumer weights and may have just dumped a whole bunch of your workload into, the performance swamp and just slowed things down because a bunch of stuff needed that parallel processing that it's no longer getting. So if you're going to change max stop, test. And when you're done that, test a few more times. All of that not in production. Don't test in prod. And if max stop 1 works for you, go with max stop 1. If max stop 1 doesn't work for you, maybe think about the cost threshold of parallelism. Am I creating a situation where too many queries are going needlessly parallel? And there are ways you can find that with Query Store. Jonathan Cahias has written some lovely queries, and I call them lovely simply because he wrote the X query, so you don't have to, and I didn't have to. Michael J. Swart has some stuff that can help you interrogate what the costs of queries and query plans are. And you can get back, what the majority of your plans are running at. And if you are, for example, and I'm making this completely up, if your cost threshold of parallelism is 40, and you have a bunch of plans with a bunch of executions that are 42, 43, 47, and then nothing until 67 for a cost, you may want to consider bumping your cost threshold of parallelism to 50 or 55. Again, test in non-prod to make sure you don't cause a problem. But as you start to look at that distribution of costs of your query plans, you may find a place that you can eliminate some of these CX packet and CX consumer weights because those plans really didn't need to go parallel in the first place. And of course, our friend statistics management. Keep them up to date and think about the sample size. Just like in the example of that I gave for thread pool, that query was going needlessly parallel because of poor statistics. What I forgot to tell you then is while it was over 2,000 before I switched the sample size, it dropped down to a cost of 2 when I switched the sample size. It was that different. There was no chance that thing was going parallel. It solved a whole bunch of problems just by getting that one query out of the way.
So there was a question on CX Packet here, and that is,
Cool.
now that CX Packet and CX Consumer are split out, why wouldn't the CX Packet be a bigger concern today versus, say,
Oh, it is.
2016?
It is, and I'm sorry that I didn't communicate that. It absolutely, CX Packet today is absolutely a bigger concern than it used to be. Again, still paired with these two weights that we're going to talk about here in a moment, really makes it a higher priority, because you with CX Packet now you're talking about skewed parallelism where parallelism could be occurring where we don't need it, or we've got work imbalance in that parallelism. I'm sorry that I didn't communicate that extremely well. As I think back, I understand why I didn't. So sorry about that.
All right,
Does that
thanks.
clear up the question?
Yep, and that was only question so far.
All right. So page access weights. Page IO Latch tells you right in the name, IO. That is about access to pages on disk. We're reading from disk into memory, because remember, SQL Server can't do any manipulations of pages unless they're in memory. The XX part of the name is a placeholder for the latch to be acquired. Typically, it's shared, so the page is going to be read. Or exclusive, which means it's going to be locked because that page is going to be changed. Page latch, without the IO, that page is already in memory, and then everything else is the same. The key part is to remember where that page is, and thus don't confuse them with each other. However, page IO latch, don't assume the IO subsystem or the IO path is the problem. It often isn't. It's something in the middle. Not necessarily in the middle, but it is often not the ability of the disk to perform. It is the ability of, or it is the pages that we're reading. Page latch, don't assume more memory. In fact, never assume more memory will fix that, because the page is already in memory. Whether you've got 32 gig in that system or a terabyte in that system, that page, and any page, is still only going to take up 8K. Also, since it's already in memory, faster IO is not going to help. Page IO latch, we can look at query plans, and we can also use DBCC page. We can determine what table and index is being read. And then we know what file it's in, and we can investigate the IO subsystem latency. Because while I said don't assume it's that to start with, I didn't say it isn't necessarily that. Right? Sometimes we investigate elimination, so we get some garbage out of the way. We can do that by looking at subsystem latency with OS virtual file stats and the average disk per second read in perfmon. When it's coupled with CX Packet and you're looking at the query plans, look for parallel or table scans. Look for, again, those long-running table scans. And I almost am tempted to move this one to the very top of the list. Look for implicit conversions. When you have an implicit conversion of data types, for those who don't know, an implicit conversion, SQL Server will convert one data type to another if they don't match. So if you're passing in an nvarchar 4000 and you're looking at a big int, that's an implicit conversion. nvarchar 4000, by the way, is the default data type in most ORMs. And many developers never changed that. So look for those implicit conversions, because with an implicit conversion, SQL Server can't really optimize the plan and look at all of the things in terms of indexing and statistics to make it a better plan. We can also check for page life expectancy or the memory pressure, because we're going to see some page IO latches with that churn of pages being pushed out and back and then having to be read, or other pages having to be read. So we can check for that. From a solution perspective, again, we're going to look at indexing. And this is where some of the stuff I talked about earlier, with the idea that, making sure we have a good indexing plan that covers our heavy hitter workload queries, but not necessarily, we don't want an index for every query. Yes, we can do 999 non-clustered indexes on a table. That's a limitation, not a goal. We also want to make sure we're eliminating indexes we don't need. Again, statistics. For all the reasons I talked about, SQL Server is going to estimate the work it has to do based on the statistics that it has and what it knows about the data distribution. And that could influence the amount of data that it attempts to read. Code change. If we don't have queries, well, first of all, the first code change piece is, of course, make sure we don't have those implicit conversions. The code changes could also be where clauses, havings, the predicate to reduce that filter. I've said it before. I'll say it now, and I'll probably say it again. We want to bring back the smallest set of data that we need. If you've got a developer that says, I want to bring back all the data and I can do it faster in memory, I doubt it. Data retrieval is what SQL Server does well. Ask it for just what you want, or just what you need, not everything. Okay. And in the end, it's possible you will have to update disk or memory. You might need faster disk. You might need more memory. But again, do the things in the software first before you pay for more hardware. Page latch. And this is a little funny to me, because we talk about Temp DB Excess, which is, yes, on disk, yet this isn't the IO weight. Because it's temporary files, it's kind of temporary, it's kind of an extension of memory. That's why it falls under that weight type. If you're using SQL Server 2014 or older, make sure trace flag 1118 is in place, so we have so we don't have mixed extents. That will help with the Temp DB problem. And again, we're going back to query plans. And as you're doing your analysis, there are extended events you can set up to look for page splits. And specifically, you're looking for mid-page splits more so than end-page splits. Mid-page splits where data is being inserted or updated into an existing page, and it has to split and create another page and move the data. And then depending on where that is in the depending on the size of the index in the B tree, it could have to split pages above it, and that becomes a problem. We can fix some of that by adjusting fill factor. Be wary, because remember, fill factor leaves empty space on pages, which is great from a page split perspective. It also means we're using more memory to hold the same data. So this is another one of those test scenarios, and don't get heavy-handed with the fill factor. Open it up a little bit and a little bit and a little bit. You may have to take the more painful step if you find your page splits are in your clustered index, of changing the clustering key. And that can be painful. And Kimberly Tripp has some great reference on what makes a good clustering key that I would encourage you to read. I'd encourage you to consume all of her stuff on indexing. Any questions?
Yeah, one quick question on that. You mentioned mid-page splits versus end-of-page splits, and is there a good way for us to sort out where the page split is happening?
I don't have it in front of me, but there is an extended event session that you can create. It's actually a pair of them. I'll try and find the link for you and send it over to you, Kevin. The extended event will find the mid-page splits and tell you what table they're in for the entire. It will tell you which databases are having the most mid-page splits, and then you can create another extended event that will investigate what tables are having the most mid-page splits. So it's a little bit of, let me find out what's going on, and then let me dig a little deeper. I just don't have that link in front of me. I should have pulled that one up. Sorry about that.
Yeah, no worries. Thanks.
But it gets a little scary sometimes when you start to look at it in an environment that is not well designed. Did that clear up your question? Anything else?
Nope, that was it.
Okay. So locks. You probably know they support concurrency. We need to make sure that as data is being changed by multiple people or multiple threads, that it's current and we're getting to the last set of the change, right? This wait is usually symptomatic. Because what's really happening is something else is making a change and it is blocking, and our query is being the one that's being blocked and incurring the lock waits. So we need to find the lead blocker, which again, the SP Who is Active tool is fantastic for that. Or you can dig through the waiting tasks and train locks DMVs. I would say Who is Active because it's a lot easier. Then you need to start examining the query plans, and we're gonna query tune at that point. This is query tuning time, and performance tuning, which are not exactly the same thing. So you're looking at, is the query written well? Are the indexes written well? It's a repeating thing here, right? Do I have good queries? Do I have indexes that support my workload? Particularly the heavy hitter frequent queries of my workload, and do I have good statistics to support them? You could, depending on your choice or depending on what the system is doing and your needs, implement read committed snapshot isolation. Be very wary of that. Very, very wary of that, because you could start reading data that's dirty, which is fine if you're just trying to approximate the queue depth of a call center. That's great. I just need something that's close, close enough for jazz is a phrase I've heard, close enough for a call center queue. If you're getting ready to send reports to the Securities and Exchange Commission, you don't want that to be close enough. You want that to be more perfect than perfect. Those folks get a little picky. And they have the power to incur some really big fines or hand out some really big fines. Transaction logs are going to wait. It's the right log wait type is transaction log waiting. Those page IO and page latch wait types are all related to the data file. This one's really common because we're doing a lot of changes, and what's happening is we're waiting for the log block buffer to be flushed to disk. So the pages that have changed out to disk, committed to the transaction log is what we're talking about, and they would also be hardened to the data file. Don't add more log files. SQL Server doesn't do parallel log transaction writes. The only time you should ever really think about adding transaction logs is when you're out of disk space on your log volume and you don't have an option to immediately add more or a way to immediately add more. And it can be a little kludgy to get rid of that second transaction log once you've got it. Avoid assuming the IO subsystem is an issue, but always check to see that it's not. Just like when we were talking about page IO Latch. It's not necessarily that, but we need to make sure that it isn't. And we may want to talk to our compatriots in storage, and we probably want to ask them to confirm it's not, rather than accuse it of being. It could be a backup of the disk queue, and that is a hard-coded max queue length. And again, we have to take some other steps to get around that. starting with index maintenance that removes those unused non-clustered indexes. So the duplicate indexes, massaging and tweaking the overlapping indexes so we can get rid of some of them. Getting rid of truly the indexes that are not being used at all. I say that with a huge caveat. Make sure that that unused index you're getting rid of is not the one that the CEO wants to see, that's in there for the report the CEO wants to see once a year, right? That big end of year report that runs in 90 seconds with that index and takes 3 days without it. Don't get rid of that one unless you can plan for it, right? If you know when that report is going to be requested, you can always do some things, 3 or 4 weeks after, drop the index 3 or 4 weeks before, put it back in. Most of the year, you're good to go. You can also, but in the end, we want to have just the indexes we need, because it can slow down our inserts and updates and deletes. Build out larger transaction sizes. Open trans and commits, so we get larger transactions as opposed to a whole bunch of little ones that are changing pages. Again, we're going to go back and hunt for page splits. And we talked about increasing the fill factor previously, and the same holds true here. Test, and then test some more. Because all of that action, every one of those things that I described before in a page split gets written in the transaction log. Therefore, it has to wait in the log block buffer to be flushed to disk. And you may have to fix it with faster disk. And fixing it with faster disk still applies in the cloud. If you're in Azure, you may have to go from premium to ultra disk, just for the transaction log. Maybe not. You might have to. You probably have to do some testing, playing around with it, to figure out what's going to go. This is one case where I'm not dragging my feet to the hardware change. I'm not starting there, but I'm a little more willing to get there. Windows waits. And I say Windows waits because the preemptive OS XX waits are specific to Windows. Linux probably has something similar. I just don't know what they're called. So this is a call out to the operating system. Something is needed that's not a part of SQL Server. So the thread has to switch to preemptive mode, and it's going to stay, and the state will still be in running, even though it's incurring wait time. And the way to find these is when you remove that preemptive OS leader, the XX, the variable, is going to give you the name of the Windows API that is being waited for. And then, follow whatever steps that you need to for that API. There's plenty of APIs. There are plenty of different options for troubleshooting those. And I'm not a developer, so I'm not even going to pretend to tell you how to troubleshoot APIs. These waits other than to tell you how to look up the API, which is find the name of it and use your search engine of choice. Now, I mentioned earlier, thread pool is my least favorite, most scary wait. Async network I/O is probably my favorite wait to see because it generally means SQL Server is processing the data at breakneck speed relative to whatever is requesting it. So SQL Server is sending the data across the network to whatever's calling it, and whatever's calling it can't process the data fast enough and acknowledge SQL Server has delivered the data. This is one of those few times where I will say it's not a network problem. It's almost never a network problem, and it's almost never DNS. Have you ever heard somebody say that? This is that rare case. It's almost never DNS. And to figure out what's happening, you've got to capture the device that's executing the query, figure out what's going on there, and do we have undersized web servers? Do we have some bad code in the processing? Are we just getting crushed on the website? Has somebody queried SQL Server via Excel or Access, which are notoriously bad when it comes to querying SQL Server and processing the data that comes back. But it's almost never the SQL Server engine itself, and it's almost never the network when we get to network wait, to the async network IO wait. And I'm happy to report we're almost to the end. So we talked about threads and thread states a little bit. We talked a little bit about weights in general terms. And we talked about those different types of weights. And while I think that the information I gave you on the specific weights is useful information, I really think that the most important parts of this session are helping you understand the thread piece and what weights are in general terms, so that you're more comfortable why SQL Server is waiting and what wait is happening when it's waiting, more so than what the specific wait type is. The weights and queues white paper is still fantastic. Paul's weight stats library, just his blog in general, is fantastic. And then Greg Gonzalez's post on SQL performance as to why weight stats are not enough are all fantastic resources for troubleshooting, as well as what not to do or do about some of these weights, again, from Paul Randall. And the thread and task architecture guide from Microsoft as it relates to SQL Server is some really deep cut nerd reading. It will cure two things for you. It will cure gaps in knowledge about thread and task architecture in SQL Server. And it's not exactly, the Lord of the Rings or quality literature. So it might cure insomnia for you too. So be careful when you read that one. All right, we're up to the last set of questions. Last time I'm asking for questions. What do you got?
All right. First, Anders says it's always DNS. And based on the number of exclamation points he says in here, I think it's a very compelling argument because there's a lot of exclamation points.
Yes, for 99.9999% of things, it is always DNS. But I'm going to disregard most of the exclamation points because it's Anders.
I mean, that is also a compelling counter argument.
Hi, Anders.
So if there are any questions for Peter as we wrap things up for the evening, now is a great time to ask. Great job, Peter. Excellent. I agree. Excellent presentation.
Thank you.
One thing that I would mention on SOS scheduler yield, I didn't jump in at the time, but you mentioned that SOS scheduler yield usually does not indicate CPU pressure. Right. And one area where you can draw some nuance is if the weights are signal weights, where for SOS scheduler yield, my recollection is signal weight indicates, hey, I'm waiting for CPU cores.
Okay.
Versus the other type. There's another type of weight which is on there as well.
The resource weight is I'm waiting for the resource, and then the signal weight's the other half of that. I'm in that runnable queue waiting to get onto the CPU.
Yeah, and so in that case, that may be an instance of more CPU cores or more powerful CPU cores could actually improve that system in that scenario.
Yeah. If you're seeing a significant depth of that runnable queue, then CPU pressure might be an issue.
Yeah, but excellent presentation. I think Anders just compared this to the Iliad. So you got that going for you.
Sorry, had to make the Homer joke since he said Iliad.
I was going to say, I think what Anders means is he's going to try to steal your girl, and then you're going to have to go invade. And
I'm married to a lawyer. You don't want to do that.
You'll get all your buddies and go to town. All right. So it sounds like no more questions in chat. Certainly appreciate you taking the time this evening to talk to us about weight stats, give us the lowdown, and appreciate all the resources.
No problem. Thanks for having me.
Of course. So as we wrap up tonight's edition of the Triangle Area SQL Server User Group's main meeting, I want to give you a quick reminder. Next week is the Business Intelligence and Data Science meeting. So come check us out for that. All meetings, as always, are at meetup.com/tripass, TRIPASS. And until we see each other again, everyone, take care.
See you, Kevin. Thank you.